Does everybody hear me okay? Yeah, good. Wave your hand if you can't hear me. Is this better? How's that? Okay. Good. Great to be here. Great to be in the opening session. I'm also from University of Manitoba, from the same lab as Khaled, actually, and I also share two co-authors, David Ahlström and Pourang Irani, my advisor. So I'll start off by saying that this is a really exciting time where we have able to realize the potential of Mark Weiser's vision of ubiquitous computing. We can do this through these new wearable devices and miniaturized sensors, and we can actually use mixed reality to integrate computing easily into our everyday activities. And we can do this in a mobile context, at home, at work, etc. And just this year, there's a bunch of devices that are now becoming commercially available that are very sophisticated sensors, and these are embedded directly into the device, self-contained. They have impressive real-time tracking and so forth. So these see-through mixed reality displays allow you to superimpose virtual content onto the real surroundings. So they're see-through, you can see the real world, but one drawback is that the virtual area is limited to within a certain field of view. And this field of view varies depending on the different hardware. So there's quite a range of different hardware with different fields of view. Now this presents a challenge for application designers that want to make an application that might be compatible across all of these different platforms. So one way that we as researchers assist application designers is by modeling. So here we have Fitts law, which is a very famous model that's been proven in lots of contexts, and we use this to predict selection time of selecting an object MT as a function of the target distance A and the target width W. And as I said, this model holds in a great number of contexts, but one context that it has been shown not to hold is something we call peephole pointing. So peephole pointing is essentially making an object selection using mobile augmented reality. So if you want to select an object on your phone, the model doesn't work essentially because of this limited viewing area of the phone screen. And this is similar to the limited viewing area of these head-worn displays. So let me give you an example. This is the mobile screen is your peephole, and I want to select an object. First I have to move the peephole to find the object in view, and then I have to make a secondary maneuver to select that object. In this case, there's an on-screen cursor to select the object. But it's the same is true with some other selection technique, for instance, with the tap. However, there have been researchers that have introduced some models that are derived from Fitts' law that are designed to handle this case. So there's two models. One is by Chow, Lee, and Balakrishnan, and a second model by Rose and Ulusvirta, and these were both introduced in the same year at CHI 2008. And these work because they introduce an additional parameter S that represents the screen size of the peephole. And we call these two-component models because they are essentially a sum of two components. The first component it measures the time to locate an object within the view, and the second component is to make the selection. So one other follow-up work I want to mention is by Kaufman and Ahlström, and they did a follow-up study where they looked at both of these models and compared them to Fitts' law, and they did this in the context of a mobile projector, so basically a projector phone, and they found that these models, they verified in this context that these models are better. Just to give you an idea, their correlation for these two-component models is about 0.9, whereas for Fitts' law it was about 0.8 if you have some prior knowledge of where you expect the target to be, and they fell to about 0.6 if you have no knowledge, if you have to do a search to scan for the target. And this isn't a 1D pointing task, of course. So the contribution of this work is we want to see if these models will hold if you're using a head-worn display. So if you're using your head motion to control the peephole as opposed to a handheld device, We do this using emulation in this cave environment. So the nice thing about a cave is that we can make a virtual peephole, and it's very easy for us to change this to different sizes. So the study looks something like this. The user stands in the center of the cave, and they see two targets. These are placed at a radius, so depth is constant in this case. So these are placed in an arc, and our parameters W, A, and S are measured in angular degrees. So it looks like this. We have a two-component task. So this is following the CLB study and the Kaufman-Ahlström study. So first the participant goes to the start target. They select the target, and now they scan until they find the first target. Okay, so this represents a case with no prior knowledge of the target. They have to scan until they locate the target. They make a selection, and now they go back to the start target, and they know where this one is. And so this represents a case with prior knowledge. This is a clever design introduced by CLB, and we followed this with two different selection techniques. So we looked at raycasting and kind of a virtual tap technique. So they look like this. So here's a participant selecting, doing these two. You see they come in pairs of two selections, these sequences. And you can see that the peephole size is changing as he goes through the task. This is just a more close-up view, and basically we just had it's essentially a mouse tracked with the Vicon tracking system, and there's a virtual ray coming from the front of the mouse, acting as a raycaster. And this is the tap condition. So the tap, we track the user's finger, and this is like a virtual touch screen. Of course, this participant is seeing it in a stereoscopic view, so it looks as though the target is where their finger is, which you don't see from this angle. So these are our factors, and we're going to look at model fitting as well as some errors in movement time. And we did a between subjects design, so we had 12 participants using each of the two different selection techniques, the ray and the tap conditions. So here's the model fitting first. So you can see that in line with the previous results, we have a much higher fit with the two-component models than with Fitts' law. And actually with Fitts' law, we have much lower fits than we did with in the Kaufman-Ahlström, whereas they had about 0.6 to 0.8. We have a much lower model fitting. However, as Kaufman and Ahlström pointed out, if you separate the S into each individual peephole size, then you actually do get very good fits for each size individually. So their argument was that you have very few cases where S is actually a variable. So your phone screen size in a mobile context is a constant, and same with the head-worn display. However, these two-component models are still useful because, as I mentioned, you may want to have an application that is compatible against multiple different platforms, and you may have a variable field of view. So one case where you might dynamically change the field of view is given by this example. So you have, this shows the number of errors, and you can see that with a larger peephole size, so NR represents our baseline with no restriction at all. So this is a baseline Fitts' law case. There are much higher error rate, whereas people are much more careful with the smaller peephole size. So you could potentially change the peephole size dynamically in a case where you want people to be more careful about making a selection. We didn't find any significant difference between the two techniques. However, you can see that with different target widths, smaller target sizes, there does appear to be some difference. And this makes sense because ray casting is known to be susceptible to jitter. So with smaller targets, the selection is a little bit slower. And we did, as expected, find a difference between in the variable of prior knowledge. So there's a difference between prior knowledge and no prior knowledge, and this again reflects the findings of CLB and Kaufman-Ahlström. And you'll notice that the effect is more pronounced with a smaller field of view. And this makes sense because, as Kaufman-Ahlström pointed out, if you have a larger field of view, some of the targets in some of the cases are going to be initially visible before the user starts turning their head. So it makes sense that prior knowledge is less important if the targets are initially visible rather than hidden. So our results are very, very much in agreement with these previous studies. Just some areas for future work. We'd like to look a little bit more at the hand versus head couplings. We noticed that even though this the selection technique is actually decoupled from the head motion, people actually in our study design acted in a very coupled manner. So as they moved their head, their ray would very closely follow their head motion. So this may have to do with their study design. It would be interesting to look into that a little bit more closely. We'd like to confirm these models on some different hardware platforms rather than our emulation. And it would also be interesting to explore some of these application designs where you can dynamically change the field of view. For example, in the case I mentioned, to maybe prevent some errors. So with that, I'll say thank you very much, and thanks for coming today, and I'll take any questions.
Thank you, Barrett. Any questions?
Thanks. Interesting work. How do you expect this to scale when the task is not one-dimensional, but essentially two-dimensional?
Well, we were initially going to look into that. We ended up not getting it into this paper. We wanted to do a two-dimensional task, but we had a lot of debate about that because in a lot of previous work, the 2D fit studies the findings are essentially the same as the 1D studies. We don't expect it to be a lot different. The big difference, of course, is in the search, right? So if you don't know where the target is, then, yeah, as you pointed out, you have to do this maybe lawnmower search or some other searching technique to locate the target initially. So, of course, this leads into the area of off-screen visualization cues and how do you lead the user to the target. And this is another interesting area that there's not a lot of work yet in the head-worn display area.
The choice of the cave was driven by, choosing the cave rather than a rift or a vibe. Was it driven by availability of the cave, or did you consider using either one of the HMDs to do the experiment itself?
That would work. We actually have a vibe in the lab now, but we didn't at the time, so it was basically based on availability. I think the vibe would be a reasonable choice, and actually the latency would probably be a little bit lower, so that might make some difference. But the other difference would be that you wouldn't have, you'd have some effects of the virtuality. So maybe I noticed that people maybe can't use the technology for as long because of maybe they'll get simulator sickness and so forth. So I think there's trade-offs to both possibilities.
Hello. I just noticed you are looking for the Peephole point, and I think you focus on at the moment you focus on maybe the head moving and the head moving. Do you think about the actual body moving will factor in? Because since you are using an example of the AR, and in AR application, usually people may walk around. So do you factor in that maybe walk around the physical body movement may give some impact with your result?
That's a good point, actually. So that's an interesting next step. So I imagine the model fitting would probably still work. Maybe you need to introduce a 3-component model or something like that, where you first turn the body and then the head and so forth. My initial guess is the results would be similar, but of course there would be some differences. So I think this kind of that's a very good kind of next step for evaluation in a more ecologically valid context, I think.
Okay. Hello. I'm afraid that's all the time we have for questions for Barrett, so let's please thank him again.